Hi everyone, welcome to video number 2 for your summer packet for calculus. And in this video, we're really going to get into what it means to find the limit of a function. And so we kind of gave a little bit of a preview of why we need limits in the first video, and we're going to recap it here. So if you look at these three functions, again, these are the same three functions that we looked at in the previous video. And the big idea I want you to get is this. Though each of the graph looks very different, in each case, f of 2, right, is equal to 4. So though that's useful information, the function value does not tell us anything about the behavior of the function close to a particular value of x, right? The function value is the same, but again, we talked about that idea of the first one is kind of a connected function. The second one is disconnected, but that function value is kind of attached to that piece. It's the closed endpoint of that piece. And here, we kind of get that disconnected just at a point, and that point has been defined somewhere else. So the fact that f of 2 equals 4 doesn't really tell us what's happening very close to that value of x. And that's why we have limits. Limits are going to help us kind of get more information about what's happening close to that value of x. So here we have some vocabulary. So a limit of a function f of x describes the behavior of a function close to a particular value of x. It does not necessarily give the value of f of x or that y value. So it's just telling us what's happening close to it. It may not give the value of f of x. So in terms of notation, here's what we write. It's going to look like this. Okay, so we say the limit of f of x as x approaches c. Okay, and here's excuse me, here's what some of that notation means. This x approaches c, this c value tells us the x value that we're getting close to. Or that we want to approach. So that's kind of where we're looking. So we're telling the x value we want to approach, and then I'm going to add something. We're going to say this limit equals L. This describes the y value we are approaching. So if I look at this example here, if I say the limit is x approaches c, so here I'm focusing on c, and I'm going to go up here, and I want to know not necessarily what's the function value, so I'm not necessarily looking for f of c, but I want to know, hey, what's happening really close to c? And I can tell really close to c, I'm getting close to this y value of L. So this is going to be our x value. Our limit is always a y value. Now you can see here, our limit, we said, was L. We're getting really close to that y value of L. However, it is not the function value. So the actual value of the function at a given x value does not affect the value of the limit. Our limit here is L, but we would say that f of c is undefined. So that limit will not always be the function value. All right. Now, when we're talking about limits, we have actually three types of limits. A right side, a left side, and a two-sided. And luckily, they are kind of just how they sound. So a right-sided limit looks at the behavior of the function as x approaches the given value from the right side. And here's how we note that. Where we just had x approaches c before, I'm going to put a little plus sign to indicate that I'm coming from the right. Now, one thing I want to be really clear on with limit notation is we always have to indicate the function name with our limit notation. So I shouldn't ever see just the limit as x approaches some number from the right. I always have a function name attached. And then we would just say the limit of f of x as x approaches c from the right. And remember, c is just some x value. Okay, the left-sided limit looks at the behavior of the function as x approaches the given value from the left side. And to indicate that in our notation, we're going to put this, and we're just going to have a little minus sign. And again, we're always going to include the name of our function. So this would just be, oops, let me get twisted here, the limit of f of x as x approaches c from the left. Now, the two-sided limit looks at the behavior of the function as you move towards the given x value from both sides. And a two-side limit only exists if my left side and my right side limits are equal. That's the only way the two-sided limit exists. If those are not equal, we do not have a two-sided limit. So in other words, a two-sided limit only exists if both one-sided limits approach the same value. All right, so the first part, I would say the first target we have here in calculus is to be able to find the limit of a function given a graph. So that's what we're going to practice a little bit here in the video, and then you'll have some practice to do on your own. So here we're going to start with some simple graphs first. So we're going to use the graphs below to find the following limits if they exist. If it doesn't exist, write do not exist and explain why. And I'll show you how we're going to write that explanation. So let's look at this function here. I have the limit as x approaches 2 from the left of f of x. So there's a few important things here. Obviously the value I'm focusing on is 2. So I'm just going to kind of draw this. Now, one thing some students get confused about is finding right and left-sided limits. So I'm focusing on 2, and all I know here is that this is the right side of 2, and this is the left side of 2. So if I'm approaching 2 from the left side, it means I want to come from here to the left and see what value I'm approaching. And in this case, as I get closer to x equals 2, it looks like my y value is getting close to 4. Now, when I look at 2 and I'm approaching from the right, now I'm approaching from this side. And again, as I get closer and closer to x equals 2, it looks like my y value is 4. So in this case, since my left and my right agree, I know I have a two-sided limit, and that value is also 4. All right, let's look at another example. Again, my point of interest here, my x value, again, is going to be 2. And I've got my right side of 2 and my left side of 2. So now I'm approaching from the left. So as I approach from the left, it looks like my y value I'm getting closer to is 4. When I approach from the right, now things have changed a little bit. As I get closer and closer to 2, it looks like here my limit, I'm getting closer and closer to a y value of 5. Now remember, we said the limit has nothing to do with the function value. As a side note here, I happen to know that f of 2 is equal to 4, because that's where the function is defined with that closed circle. But the limit does not have to be the same as that function value. My limit, as I'm approaching from the right, I'm getting closer to that y value of 5. So now, in this case, because my left side is 4 and my right side is 5, I would say for the two-sided limit, it does not exist. And this is okay, that's an acceptable shortcut for does not exist. And here's the explanation. We would say it does not exist because the limit as x approaches 2 from the left of f of x is not equal to the limit as x approaches 2 from the right of f of x. Whenever we're saying that, I'm so sorry about that. Whenever we're saying that a limit does not exist, this is the reasoning we're going to use. We're specifically stating that it's because the left side and the right side limit do not exist. And again, you can see in my notation, I've included that function name with my limit notation. All right, now we're going to look at a graph. We're going to do the same thing. We're still finding the values of limits, but we're going to do it when there's a lot more going on with our graph. So we'll go through these examples and then you'll have some time to practice this on your own. So for number 3 here, I'm looking at the limit as x approaches -4 from the left. So here's -4. If I approach from the left, I can see that the y value I'm getting close to is 0. Now I have the limit as x approaches -4 from the right. So again, I'm coming from the right-hand side of -4, and as I get closer and closer, I'm also getting closer to a y value of 0. So now when I look at number 5, you can see I don't have that little plus or minus, so that means what I'm looking for is the two-sided limit. And since my left and my right agreed, that means I had a two-sided limit of 0. Again, it doesn't matter that the function itself is undefined at -4. We're just trying to see what that function value is approaching from both sides. All right, let's look at -2. So -2, if I approach -2 here, and I'm coming from the left side, I'm getting closer and closer to a value of +2. Now if I look at -2, right, here's the right side of -2. So if I approach from the right side, here I'm actually getting closer to a y value of 0. So now in number 8, when they ask me for this two-sided limit, since the left and the right don't agree, I need to say that two-sided limit does not exist because, and again, we're going to say the limit as x approaches -2 from the left of f of x is not equal to the limit as x approaches -2 from the right of f of x. And again, as always with that limit notation, we've included the function name. All right, let's keep going here. Limit as x approaches 4 from the left. So at 4, we've got an asymptote going on here. So as I'm coming from the left side, you can see it's just going to keep going, keep getting closer to that asymptote. What's happening here is we would say our limit is -infinity, right? Because those numbers are just going to keep getting smaller and smaller and smaller. Now, if I look at 4 from the right, those are just going to keep getting bigger and bigger and bigger. So our limit in that case is infinity. So again, for our two-sided limit here, we would say, whoops, that does not exist because the limit as x approaches 4 from the left of f of x is not equal to the limit as x approaches 4 from the right of f of x. All right, now in number 12, we have to be careful here. Since there's no plus or minus, again, we're looking for the two-sided limit. So we have to remember in our heads to check for both the left and the right. So let's find this. At x equals 1, x approaches 1, so that's right here. Here's 1. So as I approach from the left side, it looks like I'm approaching a value of 1. As I approach from the right side, I'm approaching a value of 1, so I can say that two-sided limit is 1. But realize, before we made that decision, we actually checked the left and the right-sided limit. Now 13 is something new here. Now we're looking for the limit as x approaches infinity. So what we're kind of thinking about is the end of the graph. So what would happen at the very extreme end of our graph? So if I look here, this is going to keep going. And it looks like what's happening is like there's an asymptote at x equals 0. So if I could look at the extreme end, this is going to get closer and closer to 0, but never quite get there. So we would say that limit is 0. We can also consider the other end of our graph over here. This is going to keep going, and it looks like it's just going to keep increasing and increasing. So in this case, we would say our limit is positive infinity. Alright, so following this video, you have some practice to do on your own. The one thing I will caution you of is that we use function names that are not always just f of x. So here you can see I'm kind of looking at the practice. Make sure in your limit notation you're using the correct notation that's in the problems. So whether it's capital F of x or P of s, make sure you're being careful about your notation when you're writing your limits. All right, good luck, and I'll be back with the third video.